Yep.
Yeah,
Awesome.
we can see it.
All right. So, yeah, I'm just going to give a little bit of a primer on transformers. I think this is a little bit helpful. It was for me because when I go through some of the papers, when I go through some of the challenges, like this visual will always come back, in my opinion. And the architecture is pretty important when we talk about just training LLMs in general. So, just to walk through it, like this is actually the GPT-2 architecture. So, it's pretty primitive nowadays. Like, the architectures are a lot more complicated because you have you'll have like layer norms and RMS norms that come before attention and after attention. You'll have like multiple decoder blocks. You also have like different types of attention mechanisms. Like here, this is multi-headed attention, but usually you'll see like grouped query or multi-headed latent attention, which DeepSeek uses, or you'll see sliding window attention or hybrid architectures with like state space models and RNN based attention. So there's like a ton of different variants to these architectures, but this is like the most vanilla form. So the idea is that first, like you're going to have some kind of an input sequence. And right now, actually, I'm just talking about inference time. But training time is a bit different, but there are lots of overlaps. So during inference, you're going to have some kind of input sequence, and you're going to have a tokenizer that's going to break up that input sequence. And the tokenizer is trained separately from this training process. That's usually using like byte pair encoding or other techniques. So those are like pre-trained tokenizers that are trained to pretty much take in strings and split them up into tokens. So once you do the tokenization, you have like these 6 tokens, for example. And the first step is you're going to do this embedding lookup. So that's usually the first layer of your transformer. So yeah, and sometimes you add positional encodings right to these embeddings. Sometimes when you use rope, for example, you do this at a later point, like right during attention itself. But I don't think positional encoding matters that much for this. But yeah, so you have like some embedding lookup table that pretty much maps these like tokens into vectors, and these embeddings are these are like architectural decisions in terms of like what embedding dimension you set, but here it's set to 768. So now for each token, you have a 1 by 768 vector. And then you have these KQV weights, and this is kind of the heart of where attention comes in. The KQV stand for query, key, and value. And these matrices are D by D, where D is the embedding dimension. So in this case, if our embedding dimension is 768, you have 3 separate KQV matrices, which are 768 by 768. So now when you take this embedding matrix, you're going to do a matrix multiplication with this matrix with your Q weight matrix, your key weight matrix, and your V weight matrix. So now you're going to get a Q matrix that is 6 by 768. You're going to get a key matrix that's 6 by 768 and a V matrix that's 6 by 768. So in this visual, they're all like kind of concatenated into one big matrix, but in reality, these QKV matrices are actually separate. Um, and then here now, once you have these KQV matrices, this is where the heart of attention comes in. So you do these matrix multiplications, your Q times K transpose. That's what this dot product is. Then you do some scaling by your embedding dimension. So Q times K transpose over the square root of D sub K, where D sub K is the embedding dimension. Then you add this like causal mask. And this is yeah, just done to make sure that tokens at a particular position can't attend to tokens in future positions. Um, yeah, to prevent any like look ahead biases from being in the model. And then finally, you do a softmax, which allows you to get a probability distribution over these rows. And then you do these MLP layers, these up and down projections. And then finally, so during training, actually, you're gonna like, or first during inference, you're gonna take the last token of your input sequence and you're gonna do an output projection. So this is like another MLP layer where this dimension is 768 by 50,000 and 50,000 is actually your vocab size. So this is you get your output embedding by doing um, over here. Yeah, where do we get the output embedding? That would be the output embedding. Yeah, it would be right over here. Once you get your attention matrix, You multiply by your value matrices and you get these 6 by 64. We have 12 attention heads. So once you concatenate these vectors across all heads, you get this 1 by 768. And then you do this MLP projection, and then now you have once you apply like softmax, or you pretty much get a probability distribution over your vocab, and you choose the token with highest probability, and that's how you get your next token. So during training, you're actually going to be doing this output projection for each of these tokens, and you're going to be computing like cross entropy loss that is averaged over all of these tokens across all of the sequences in the batch. So yeah, this is kind of transformer in a nutshell. And the parts I want to focus on are kind of the activations. So when we talk about activations, and um, activations are important during training because I guess so. First, when I talk about activations, like I'll give you some examples of activations. So an activation could be all of these scores in your attention matrix. These could be activations. You could also have all of these, the output uh, matrix that you produce after multiplying your attention matrix with your value matrix. These are also activations. In each of the MLP layers, when you produce outputs, like these expanded embeddings, when you do your up projection, these are all activations. So all of, even over here, when we compute our logits, before we feed them to the cross entropy loss, these are also activations. So all of these need to be stored in VRAM during training. And the reason for that is I kind of put an example together in Desmos. But if we think of a neural network, it's just this big composite function. So we can think of it as like h of x equals f of g of x, where g of x is the inner function, which could be some b beta would be the actual parameter of the network. X would be your input. So this could be a two-parameter network where g of x is beta times x squared, f of x is root alpha times x. Beta and alpha are our two parameters. So now h of x, when you apply the composite function, you get this over here. So now if you want to find like the partial derivative of this h of x with respect to, let's say, alpha, right? That's going to be 1 over 2 root of this argument times the derivative of this with respect to alpha, which is how you get beta x squared. So this part is really important because this is actually what's going to be used in gradient descent when you do your back propagation. And if we look at this derivative over here, it's actually in terms of this beta times x squared is g of x. And this root alpha times beta x squared, this is f of x, where x is beta times x squared. So the point is, like, this derivative is actually in terms of the outputs of each of the layers in the network. So if we go back over here, like when we do our back propagation, we're going to need these outputs of each layer to compute the derivatives with respect to the parameters of the network, especially when you're in earlier layers of the network. You're going to need activations. You're going to need even more activations from all the later layers in the output. But if you're at a later layer in the output and you're trying to update the parameters, you don't need as many activations stored. So hopefully this idea of activations makes sense. And yeah, and there's like a lot of stuff. So the reason I bring this up is because like memory is one of the hardest things to manage when you're doing long context training and training in general. And there have been tons of techniques over the years like to manage memory during training. So like this one by Microsoft, ZeRO, the zero redundancy optimizer, like this paper is all about how we can use like different types of sharding techniques to pretty much split like different parts of the model across GPUs. So it's like a distributed training technique. And they actually talk about how somewhere they talk about the main things that eat up memory. I highlighted this somewhere. Yeah, so over here, for large models, the majority of memory is occupied by model states, and model states include optimizer states. And the optimizer states, like if we talk about the atom optimizer, it has like our first and second moments, which are like the variance or the mean of the past gradients and the variances of the past gradients. So you have to store those for every single parameter in the network. So this eats up a ton of memory, especially if you're using like BF16 or FP32. Then you also have a bunch of memory that's eaten up by activations. And we're going to come back to activations a lot through this session. But hopefully now, like you understand that when we're talking about activations, these activations actually refer to the intermediate outputs in our decoder, in our transformer. Um, and then we also have memory that's eaten up by like these temporary buffers that PyTorch allocates, especially when you're training on like variable length sequences or dynamic batch sizes. So yeah, most of what Deepspeed ZeRO targets is actually sharding these model states. So this is going to include um, your optimizer states, your gradients, and then your parameters. So this is something that we've already integrated into our training pipeline. And you can actually configure this by selecting different stages of ZeRO. So ZeRO stage one just shards your optimizer states. ZeRO stage two shards your optimizer state and gradient states. And then ZeRO stage three shards all of these. So just by enabling ZeRO 3 when you're using multiple GPUs, you can already get a lot of memory freed up for longer context training. And you can actually run this experiment yourself, where if you drop down to like 0.1 instead of 0.3 and you try to train on the same sequence lengths, you're probably going to get out of memory. So yeah, you can run that experiment. But this is one optimization that we've already integrated. Then there's also like other stuff that people have researched into. Um, so this includes like this is actually a DeepSeek V2 paper where they talk about their like new attention mechanism that they designed called multi-headed latent attention. And the idea over here is like how do we so a lot of times what people have done over the years is they've come up with these new attention techniques. So it all starts with multi-headed attention, which is like what I explain over here. Um, but there's like group query attention, multi-query attention, where all of your queries will share like either groups of keys and values or just one key and value. But the idea here is actually mostly for inference. It's mostly to reduce the size of the KV cache. But there are also implicit benefits during training, because during training, you have to store less parameters, you have to store less activations. So one thing that we've been exploring is just using models that are using these newer attention techniques. That helps a lot with both training and inference speedup. So all of the models we're using right now, like Qwen 332B, even Gemma, they're all using like different variants of like GQA, MQA, and MLA. Like Gemma, for example, uses sliding window attention, which is another technique. But the point is like there's other research that goes into how can we save memory more from an architectural perspective. ZeRO is more about from a parallelization perspective and through sharding of optimizer states and parameters. And then this paper and all these other techniques like GQA and MQA are more from an architecture perspective. How can we save memory during both inference and training? Then there's also stuff like flash attention. So flash attention is also huge because it pretty much identified that like when you're computing attention naively, a lot of times like the attention is actually computed in your it's actually using like the L1 and L2 caches in the SRAM of the GPUs. So a lot of times like the SRAM is not actually your main GPU memory. So like when you look at like an H200 that has like 140 gigs of VRAM, that is not referring to the SRAM, that's referring to the DRAM. And a lot of times when you're computing attention, you actually have to go back and forth and do these IOs from SRAM to DRAM. So flash attention is all about how can we reduce the number of IOs across the network. And they use these techniques like kernel fusion. And this was inspired by like NVIDIA had this paper on online softmax where they pretty much fuse the computation of finding the maximum number in a row and computing the normalization factor, because those are the two kind of attributes you need when you compute softmax. So they fused both of these operations into one kernel. So like flash attention takes that idea from the online softmax paper. It also does stuff like selective gradient checkpointing, and they talk about this somewhere. I think I highlighted it somewhere, but they do, yeah, right over here, they do some selective gradient checkpointing. But the idea is that in the backward pass in attention specifically, instead of saving the activations, and again, you need these activations when you do your backward pass and compute the gradients, because the gradients are in terms of the activations. So instead of like saving these activations in flash attention, they actually recompute them. And they see that even though you're recomputing, you would think that there's that's going to take extra time, but actually recomputing them, when you use their technique of like block matrix multiplication, and you don't actually materialize your attention matrix in your DRAM, it's actually a lot faster, and you actually like don't even need the overhead of recomputation still reduces time. So that's kind of the idea of flash attention. So something we're working on as well is implementing like flash attention 4. That's supposed to also help with training, especially on Blackwell architectures. So that's something that also helps with long context training. So you might notice if you use like SDPA as your attention implementation or flash attention, just by using flash attention, you're going to have more VRAM available, leading you to train longer contexts. Um, and then there's also some work that goes into this is like a very different paper, but this is more about not even like training techniques from like architectural perspectives or parallelism perspectives. This is more about like data sets, creating data sets for long context training. So in this research, which I found that was pretty interesting, this one I think is by Princeton, but they were talking about how, like, if you only train on long context data during CPT, that actually hurts the model during short context settings. And during SFT, they found that you actually don't even need long context SFT data. As long as you implemented a long context CPT training stage, short context SFT data is sufficient even for long context settings and inference, as long as you've done one long context training stage, either during pre-training or CPT. So these were like some findings they found here, more around data generation for long context training. So I think this paper is kind of relevant as well. Um, and then now this kind of dives into sequence parallelism, which is the main technique that I've been reading into for long context training. So sequence parallelism, this idea came to be in like May 2022, and yeah, it was originally developed in Singapore. But this paper is just what introduced the idea of sequence parallelism, and they came up with this attention mechanism called ring self-attention. And there are many variants of this, like the one of the most popular ones. If you guys have ever like read into different attention techniques, there's something called ring, I think it's ring block attention. This is like a pretty famous paper from UC Berkeley. But this one was actually one of the first papers to apply this idea of ring attention and sequence parallelism to transformers. And then over the years, there have been many improvements on this. But this leads into the paper that I actually read in a lot of detail that came out last year. And this is called Arctic Long Context Sequence Training. And this is using many of the ideas of sequence parallelism from past research. But this is by Snowflake, and their goal is pretty much to integrate this stuff into the Transformers ecosystem by Hugging Face, because there are many different implementations, and they talk about this somewhere here. Yeah. Uh, Second, training with multi-million sequence lengths requires more memory than available in any commercially available GPU devices. And while there are solutions that allow for leveraging aggregate GPU memory across multiple devices, and these solutions are like the ones that I mentioned, the one by Berkeley, the one by the Singapore University, many different variants of sequence parallelism that have come out. Their claim is that first, ring-based sequence parallelism does not support arbitrary attention patterns natively. So the idea here is that it's hard to use both flash attention and ring attention in parallel. So this was one thing that they wanted to overcome. And then there's also something like Deepspeed came up with a technique called lasis or lasis. I don't know exactly how to pronounce that. But this is a different variant of sequence parallelism. And this is very restrictive to like when you use Megatron or if you use Deep Speed only for training. But given that we're using Hugging Face transformers, it's really before this paper came out, it was very hard to find like sequence parallelism implementations without writing your own monkey patches. So this paper kind of commoditized sequence parallelism in the Hugging Face transformers ecosystem. So yeah, this is the paper that I focused on. So some things that they talk about here, and this is very similar to the ZeRO paper in some ways, right? Where they talked about how GPU memory is used for these different things. GPU memory is used for your weights, optimizer states, and gradients, and this eats up the bulk of memory. But with ZeRO 3, we've kind of taken care of this problem. But the trade-off is that we have a little bit more communication overhead. Um, but we're willing to accept that if we need to train larger models and longer contexts. The second part of that takes up memory is activations, and we've talked about this idea of activations. And then finally, we have these runtime overheads. So this includes like the buffers that PyTorch and NCCL create when you're using like dynamic batch sizes or variable length sequences. So these are all like big consumers of VRAM. So what they found is that, and this kind of makes sense. What actually happens is that when you train on longer sequences, these two things, these two parts of memory are not the ones that explode. It's actually the activation memory that explodes. And this should kind of make sense because if we go back to this visual over here and we look at this attention matrix, the shape of this matrix is very dependent on your input sequence length, right? So if our input sequence is 6 tokens long, then our attention matrix over here, which has all of the activations that we need to store for the backward pass, this is a 6 by 6 matrix. But now if you're training on like 10,000 K sequence length or 100,000 K sequence lengths, like this is going to blow up. So, and this is exactly what has your activations, which you need to store in VRAM. So that's where they get, that's why they're saying over here that now that you understand what GPU memory is used for, it should be easy to understand that in order to go from a short sequence length to a long one, it's mainly more of the activation memory that we need to fit. All other allocations remain the same regardless of the sequence length. And then they show this also with Llama 3.18b, where like if you increase your sequence length, your memory usage goes up as well. And this is also what I see in some of my experiments that I'm going to show you guys as well. Um, but yeah, the idea over here is that they have many different techniques, and to be honest, I don't understand all of them in detail. But some of the ones that I do understand, and I think this idea over here is a little bit important in some ways, because, so yeah, I'll just explain it. So what they do is, maybe I can go back here. So with sequence parallelism and their implementation of sequence parallelism, what they do is they first you have like let's say we have 8 GPUs and we want to shard the sequence across or actually we have 6 tokens here. So let's say we're using 6 GPUs and we want to shard our 6 tokens across 6 GPUs using sequence parallelism. So before we get to attention, what we're going to do is all the computations up to attention, we're going to shard each token, since we have 6 tokens, 6 GPUs, and we're sharding across to all 6 GPUs, the sequence. We're going to send each token to each GPU. So data will go to GPU 1, visualization will go to GPU 2, M will go to GPU 3, and so forth. And now each GPU is going to do its operation. So to everything up till attention. So you can't really see that here, but usually all the layer norms, the RMS norms, any kind of MLP layers you have before attention, those are all done independently on each GPU. And that's the first thing they're saying over here. Starting with sequence parallelism, the sequence is split across participating GPUs and executed in parallel until the attention block is reached. So now when you get to the attention block, what happens is, depending on the number of attention heads that's in the architecture, now you switch from sequence parallelism to attention head parallelism. So if you have 6 GPUs, the first 2 heads will go to GPU 1, the second 2 heads will go to GPU 2, the third set of 2 heads will go to GPU 3, and so forth. But now we're not actually sharding across the sequence dimension anymore. And the reason for this, from my understanding, and that's what they say over here, since self-attention requires an entire sequence, at this boundary, we switch from sequence parallelism to attention head parallelism. Um, so yeah, flash attention actually computes the self-attention in blocks. So here they're saying self-attention requires an entire sequence, and I don't think this is entirely true, because anyways, when you do flash attention, it's splitting up your sequences in blocks. But if we go back to the very beginning of the paper, they said over here that um, ring-based sequence parallelism does not support arbitrary attention patterns natively. So I think the idea here is that if you shard against the head dimension, you're kind of attention implementation agnostic. So you can use ring attention if you want, you can use flash attention if you want, you can use SDPA, you can use any kind of implementation. Um, so I think that's why they switch back to attention head parallelism for this step. Um, yeah, but that's still kind of a gray area for me. And then after attention, then you switch back to sequence parallelism. So now you're sharding again over the number of input tokens or your sequence dimension. So yeah, that's kind of the steps they follow for sequence parallelism. And this idea is kind of important because when you train, and I'm gonna write some docs on this, but uh, when you set the sequence parallelism shard size, that actually has to be divisible by the number of attention heads. If it's not, you're going to get some kind of an error by transformer saying that, oh, your SP size is not divisible by a number of attention heads. So before you do any kind of sequence parallelism, you probably have to look at the actual model architecture. You need to know how many attention heads it has, and you need to set your sequence parallelism size so that's divisible by the number of attention heads. And that's because of this step over here, because we're switching from um, sequence parallelism to this attention head parallelism. Um, yeah. So now, I guess before I move forward to the experiments, are there any questions? Sorry, I know maybe some parts of this were confusing, and a lot of it is still confusing for me, and I'm still learning, to be honest, but just trying to share everything I've learned along the way. But yeah, if there are any questions, I can take them now. Otherwise, I can move on to some of the findings from some experiments I ran. Yeah, Aditya.
Yeah, yeah, you mentioned that first there's like a sequence parallelism, and then after that we go to like attention head parallelism. So that will include like a lot of data going back and forth between the GPUs, right? Or if it's a multi-node setup, then that transfer of data will also be part of that, right? So it'll be comparatively a slower training. Is that right?
Yeah, yeah. So I'm gonna touch on this a little bit, but similar to like zero stage three, like there's always a trade-off. Like if you want sequence parallelism and you want longer context training, there's more sharding, there's more parallelism, which means more all gathers, more reduced scatters, more communication costs. So it's definitely going to slow down training a bit. It's a little bit hard to quantify that, but yeah, training will be slightly slowed down from
No.
my experience.
Yeah,
So
the
yeah.
reason I'm asking is because it'll happen like for each mini batch, right? Because you'll have to do it at each step whenever you're going for a forward pass.
Yeah, it'll happen definitely during the forward passes and during the backward passes. Like
Okay.
you're gonna have reduced scatters and all gathers at both of those stages. Yeah.
Okay, yeah, that's all I wanted to ask.
Yeah. And actually there are like some NCCL environment variables that you can set in our bash script where you can actually like see all of the collective operations that happen during training. So that's something interesting. I didn't actually report any of that here, but if you're curious, you can actually see like when do your all gathers happen, when do your reduced scatters happen, um, and so forth. But yeah. Uh, okay, so in this experiment, as I mentioned, the goal of this is like up till now we've pretty much only been training all our models on like under 10K context lengths, and a lot of times like in our CPT data, like sometimes we've even had documents. that are up to like 1 million tokens. And sure, those are outliers for sure. But a lot of times, like we have a fair amount of our data that's in the hundreds of thousands of tokens, or even, or at least above 50,000 tokens. So I think it's pretty reasonable to train on long sequences. And I think that's a requirement that we should implement. But with that said, and to your point, Aditya, if you're training, if you know that all of your documents are under 10K, there's no point at all to enable sequence parallelism. That is just overkill and it will slow down your training. So I wouldn't recommend that at all. So that's why I probably will set sequence parallelism to false as a default, and you can enable it if needed. Yeah. So this is kind of the motivation of sequence parallelism. We want to enable longer context training. Um, okay, so uh, I'll just talk about the experiment a little bit, but I ran 640 different experiments on sequence parallelism, and this is kind of like a hyperparameter sweep that I did across these different configurations. So I sweeped across these variables, number of GPUs going from 1 to 8, data parallelism going from 1 to 8, sequence parallelism going from 1 to 8. And the reason I had to include data parallelism here is, and this is something I don't fully understand right now either, but the way that ALST, like this Arctic long context uh, or sequence training, is implemented, they have this constraint that data parallelism size times sequence parallelism size has to be the number of GPUs. So you can't just arbitrarily set sequence parallelism size without ensuring that your data parallelism size is set and the product of these two equals number of GPUs. So that's why I had to include this other variable here. Otherwise, I just got a bunch of different errors. And then I also included, yeah, and then obviously sequence length. This is probably like the most important variable in this experiment. And then finally, I included another variable, which is batch size. And this, I don't know exactly why I included this, to be honest. I just also feel like sometimes, like, if we want to increase training speed, we'll train on larger batches. We get to see more samples in one training step, so we have less training steps altogether. And then also, um, with larger batch sizes, you have better gradient estimates, which may or may not be a good thing. In some ways, small batch sizes allow you to maybe add in more stochasticity, which allows you to like overshoot any local optima that you find in the loss function. But in other ways, like if the batch size is too low, you could have too much volatility in your gradient steps or your gradient update steps. So yeah, I just wanted to play around with this as well. Um, Something else I should note is that with each experiment, I only ran it for a few seconds, and I all I wanted to do was capture. So I'll show you the things I captured for each experiment. I wanted to capture if the experiment failed and I got out of memory. I wanted to capture um, how much memory was trying to be allocated before the GPUs ran out of memory, how much memory is free. And this is where we can kind of look at things like memory fragmentation. Um, how much memory is already allocated on each GPU. So this is like how much memory is trying to be allocated, and this is how much memory is already allocated. So this is like by the optimizer states and the model parameters. And then how many is reserved but unallocated. So actually, sorry, this would give us an idea of memory fragmentation. But this one is how much is free and how many gigs we tried to allocate. So I captured all of these like memory statistics here. And then if there was a success, what I captured is the actual GPU memory that was used. So I used NVIDIA SMI to capture this. And then I captured the training time, so seconds per iteration for each training step. So as we can see here, most of the jobs failed. And this kind of makes sense. So I'll get into this, but yeah, almost all the jobs failed, but it's very interesting to look at these numbers. So I made some plots here, but before I get into the results, let me just see if I'm missing anything else that I wanted to share. Yeah, these are like the other hyperparameters that were kept constant, no changing at all. So the batch size, obviously, this was swept. the sequence length, this was also swept. Stuff like optimizer, learning rate schedules, um, all any of this other stuff like epochs, packing strategies, and so forth. Like none of this stuff was changed at all. But yeah, if you do change these other variables, like if we use SDPA instead of flash attention, like I imagine we're going to get out of memories even sooner on even smaller sequence lengths. Um, Something else I didn't look into was so yeah, actually, sorry, I'll just stop there. And yeah, this is the script I used for running the sweep. So yeah, if you want to replicate this, you can look at this document. Um, okay, so now for results. Um, so I guess first of all, just to summarize all of the results in this is like a weights and biases type of looking plot. And I think it's kind of a nice visual that uh, summarizes everything. So if we look at the color over here, the color pretty much tells us throughput. So higher throughput is better. This means that we're seeing more tokens per second. Lower throughput is worse. And if there are any crashes, we pretty much get zero throughput. So I guess first of all, if we look at um, all of these experiments that have high throughput, and we try to trace back and we look at what are their sequence parallel sizes. So let me just move that here maybe. I think this would be useful. If we look at, yeah, all of these runs over here, we are not able to get max throughput with uh, no sequence parallelism. So in other words, if we set sequence parallelism to 1, which means there's no sequence parallelism at all, and there's no sharding at all, uh, we pretty much get out of memory for almost every single run, starting from 10K to 80K. So we can't even train 10K sequence lengths if we use sequence parallelism degree of 1. And keep in mind that you might have been able to use 10K in your training runs because you were probably using like H1, H200s. But one thing I didn't mention is that all of these experiments I ran on L40 SGPUs. So each of those has like 20 to 30 gigs of VRAM, much smaller than H1, H200s. And I was using like 8 of those. So much, much less VRAM compared to what you guys are probably using during training, the P5 and P5 ENs. So that's why maybe you've been able to use longer contexts. But yeah, over here, the only way we can get these high throughputs is if we set sequence parallelism to a high number. Um, and yeah, like we consistently see that as we increase sequence parallelism, or as we increase the context length over here, it gets harder and harder to not get out of memory. In fact, we're not even able to train up to 80K sequence lengths. With even a sequence parallel size of 8, we get out of memory. So if we're using P5, P5 ENs, I'm almost positive we'll be able to support this, but I haven't actually tested it. So this is like one of the limitations of this study. But in theory, I would think that we could even train up to like 150 to 200K sequence lengths on P5 ENs, especially if we're using like 8 nodes. So yeah. Um, all right, so I can jump a little bit into the other plots. Over here, we also see that as we increase our sequence length, we're obviously consuming more and more VRAM. But if our sequence parallelism size is higher, we're able to we get out of memory much later. So if our sequence parallelism is set to like 2, for example, we get out of memory right at 20,000 K context, training context length. But if it's set to 4, we get out of memory at 40K context. And if it's set to 8, we get out of memory at 70K context. So we see the same kind of trend here. As you increase your sequence parallelism size, you can train on longer sequences and you get out of memory much later. Um, and yeah, over here, we also see that we have much higher throughput with sequence parallelism. This makes a lot of sense, in my opinion. I think it's kind of self-explanatory. So this part is very interesting, and this might touch on one of the questions you were asking, Aditya, the sequence parallelism slow down training. And my hypothesis all along, and I still feel like it does, like training time should be slower with sequence parallelism because there's more communication. But in this particular experiment, we actually see that when we set sequence parallelism to 4 or 8 versus 2, like actually the training time per step is lower. But on the other hand, the batch size is also smaller. So I don't know. This is a trade-off in some ways because when you use more sequence parallelism, you have less data parallelism. And when you have less data parallelism, um, you are using smaller batch sizes. So your training steps should be smaller, should be faster, but there's more communication overhead from sequence parallelism. So I don't really know how to reconcile this trade-off. I don't really have a clear answer here, but by this particular picture, it suggests that more sequence parallelism actually is not leading to higher training times. Um, Maybe from 4 to 8, there's a slight increase, but compared to 2, sequence parallelism 4 and sequence parallelism with 8 is actually slower or is actually faster than when we use sequence parallelism size of 2. So I think this is interesting. I don't know how true this is, but this is what I found from my experiments. Um, yeah, but I'm curious if you guys like find anything that contradicts this. Uh, Yeah, and a limitation might also be because I pretty much terminated the training after maybe 1 or 2 training steps. And usually this training time estimate is very volatile in the beginning of training. It starts to stabilize after you have a few training steps. So maybe after 10 or 20 training steps, this estimate becomes a lot more um, accurate. So this is a limitation because I terminated early. Maybe these numbers aren't even accurate. Okay, I know we're almost at time. So maybe one last thing I'll talk about with the plots here, and then I'll show you guys a really quick demo. I thought this was also interesting. So over here, we see that there's a lot of fragmented memory. So the way that you can interpret this plot is that um, when you get out of memory, you actually will see an error message from PyTorch, and PyTorch will tell you, oh, I tried to allocate this many gigs of memory, and there was only so much of this memory that was free, and this much is allocated, but there's actually some memory that is reserved but unallocated. So this is like the fragmented memory. And unfortunately, like this is actually the worst case scenario where you have like 5 or 4 gigs of memory per device that is just free, but it's not used because it's fragmented. So there are ways to get around this, and they actually talk about this in their paper as well. And this is something that I'm also going to push in the next iteration of the code. But somewhere they talk about this, how to prevent memory fragmentation. You can set one of these like PyTorch environment variables. Um, this expandable segments equals true, and this allows for like dynamic memory allocation. So this is supposed to help a lot with these fragmentation issues that I was seeing when I don't set dynamic memory allocation. So I found this to be pretty interesting. Um, okay, so with that said, I'll just show you guys one quick demo of sequence parallelism. So I am first going to show you guys what happens when we run out of memory. Uh, so I'm just launching a training script. Yeah, sorry, Mohammed. I'll be done in like the next 5 minutes tops. That's it. Yeah, it takes a few moments, but um, maybe while this is running, I can show you guys what happened on the last run. But we'll see the same thing happen here. But pretty much you get this torch out of memory error from PyTorch, and it tells us try to allocate this much memory. This GPU has this much memory that is allocated already, and only this much is free. Um, Okay, I lost that because now the training job is in progress. And yeah, so we've got the error. Uh, so yeah, as I said, this much is free, this much is trying to be allocated. Um, the total capacity is this. 19 gigs is currently in use. And then Yeah, of the remaining 18 gigs, which is 22 minus 4, there is 18 that's actually available by PyTorch. And um, yeah, 268 megs is reserved but unallocated. So this is kind of the fragmentation that I was talking about earlier. So actually in this run, which is interesting, so what I did is actually disabled activation checkpointing. So activation checkpointing is something we enable by default. And as I mentioned, if you checkpoint these activations, which means that you recompute them in the backward pass instead of storing them in VRAM, you save a ton of memory. And over here, I'm going to do nothing except just enable activation checkpointing. So if I set this to true, we can run the same training job and we'll see with the same exact sequence length, we won't run out of memory. And this sequence length is 8,000. And in the run after this, I'm going to bump this up to, let's say, 60,000. Um, and I'll show you that we can actually train. Yeah. So yeah, now the training has started. We don't actually, no, the data set is still being processed, but yeah. So yeah, now the training has started, right? Just by enabling activation checkpointing, we save a ton of memory and we don't run out of memory as we did before. Now in the last run, I'm showing you that I've enabled sequence parallelism and I've set the max sequence length to 60,000. And usually you would run out of memory if you try anything above 10,000, honestly. Um, but now we won't run into that issue. So yeah, I guess since we're pretty much out of time while this is running and you guys can see the output, does anyone have any questions? Um, yeah, Aditya?
The experimentations which you have carried out, these are on single node multi GPUs, or have you also tried out on like multi nodes?
Yeah, single node right now, but
Okay.
it
Do you
only be
think we'll ever
then.
be able to like do it on multi node because there's like a much longer wait time, right, for the scatter and gather?
Yeah, I mean that's true, but definitely we'll be able to do it on multi-node. It's just I didn't test on that, or I actually didn't test in these local experiments on multi-node, but I've ran a few runs using training jobs on multiple
Okay.
nodes. So I'll push the code for that in the next week. But yeah, we should be able to apply this to multi-node setups as well. Yeah.
Okay.
I just don't know if we'll see this same kind of pattern on multiple nodes where with higher sequence parallelism, we're actually observing lower training times. So to your point,
Right.
like with multi-node, we have like InfiniBand, which is much slower. So I imagine the networking is going to take a lot more time, and I don't think we're going to see this. But yeah, that's an open question. Yeah. Yeah, and as you can see here, now training has started. We're using 60K sequence lengths. So, yep. So yeah, next steps, I will push the code for sequence parallelism. So if you guys like pull the new training notebooks and scripts, you should be able to enable this stuff pretty easily. I'll add some documentation as well. And if you're curious about any of these experiments, like we have this in our Nova repo in the tech specs. There's a document called CPT SP, standing for sequence parallelism sweep. So yeah, feel free to look at them. And yeah, if you have any advice or feedback as well, or any other findings, like I'd be really curious to learn from you guys as well. Yeah. Um, cool. If there are no other questions, then I will stop my section and yeah, feel free to take over, Mohammed. Thank you guys.